So what are the uses of control channel? One is, of course, I'm focusing on PDCCH. Downlink control channel is used for both downlink and uplink scheduling graphs, essentially to tell which users are allocated in the uplink and the downlink, because base station is the master. Okay, we also this control channel is also used to send control information to demodulate data channels in the downlink. For example, it will tell you what is the modulation it used, what is the coding it used. Similarly, it will also indicate what is the modulation coding that has to be used in the uplink. Okay, so everything is determined by PDCCH. Okay, and what are the power control, what is the MIMO precoder matrices to be used, all those things are told by PDCCH. Okay, I was indicating what I was yesterday where we stopped was control channel is an L1 layer. What do you say? Signaling. Okay, it does not come from LTLS. Okay, I mean, logically that means that this channel entirely is generated in the physical layer. Of course, the information how to populate this channel comes from the higher layers, but that said that unlike PDSCH, where data actually comes from L2 and L3, most of the data that's required for PDCCH is generated in L1. Okay, of course, with the help of other layers, that's always there implicitly. So let us start with the. So let us start with the first thing on the transport channel of PDCCH. Okay, so here is where some masala is there. So this looks very similar to what is there in PDSCH. This is what, so there's a CRC. After CRC, there's an interleaver. This interleaver is the new block. I'll tell you what this interleaver is. This interleaver is a new block. Then of course this. Sorry. These both are new blocks. Interleaver is not a new block. Then there's a polar code. Then there's rate matching, and there's scrambling and QPSK modulation and other things. Okay. So I hope all of you remember what is rate matching. Rate matching means essentially how many ever you have a certain number of bits that are generated by polar code or any SEC, and then what you do is you have to fill up a certain number of blocks or symbols. What you do is you somehow make sure that you extend it, you increase it by using a cyclic buffer, or you do puncturing to get the exact number of bits so as to fill your resource. That's what rate matching is. Okay. So here is something that that's very specific to PDCCH. PDCCH channel. So when we generally in the PDSCH channel, when we add the CRC, we don't do anything. The CRC and the data are treated same, and they're sent out in to the polar encoder, to the LDPC encoder. Whereas in PDCCH, it is a little bit different. So in PDCCH, what they do is, so they take the CRC and they scramble the CRC with a specific something called RNTI, Radio Network Temporary Identifier. Okay. So what this means is, why do they do that, and what this means? Okay, let's discuss this. So this is a 24-bit CRC. What is meant by scrambling? Essentially, scrambling means essentially XOR with a known sequence. Okay, you XOR with a known sequence. Okay, so how is the sequence generated? Here, the sequence is nothing but the RNTI value. So, for example, every UE has an RNTI, specific RNTI called UE RNTI. Okay, CRNTI. What they do is, why do they do this scrambling with RNTI? Okay, okay. So this sorry, just hold on 1 minute. Okay, this is because of the following reasons. So the base station is sending out control information. Okay, so the base station sends control information. How does the UE know whether the control information is intended for it or for some other UE? Okay, the way this is done in the 5GNR is that you scramble the CRC with a particular RNT. Okay, for example, the two users, one user has an RNTA of 10 and the other user has an RNTA of 20. Okay, what you do, you scramble the CRC with 10. For example, this whole PDCCH is meant for user 1, so you scramble the CRC with 10. Okay, and you send it off. then what will happen? Both the UEs will be able to come all the way to, they will decode everything, they'll get the CRC, and then they'll check the CRC. They'll unscramble with their own RNTIs and check the CRC. Okay. So what will happen? The user with 10 RNTI will be able to unscramble it correctly, and his CRC will be correct. Okay. Whereas the user 25, he will unscramble with 25. Of course, unscrambling will become wrong. So hence the CRC that he achieves will be wrong. And what will happen because of that? He will think that, at least he will think that this data is not for his for that particular for me, and he'll discard that PDCCH. Okay, where the user then will use that particular PDCCH to do the next steps. Does that make sense? Any question on this? Okay. Hello. Did you understand this? Okay. Is this clear? Any question before we proceed?
Can you explain it again, sir?
Okay. So let me just show it on my iPad. Just hold on 1 minute. Okay. So you have user 1. Okay. User 1 has an RNTI of, for example, 10. Okay. 10 means it has some big representation. 10 means some big representation. 1, 0, 0, 0, 0, 0, 0, something. Last numbers will be some numbers 1, 0, 0, 1 or something. Okay. 1, 0, 1, 0 or something. Okay. Similarly, user 2 will have 25, for example. He will also have certain bit sequence. Okay, certain bits. 25 converted into some bit sequence. So what is the base station want to do? The base station want to send this control information to user 1. This control information is intended for user 1. Okay. Okay. But the user 1 and user 2 don't know whom it is sending the control information to. Only the base station knows. So what will the base station do? The base station, this is the control information, and to this it's added 24-bit CRC. Okay, this is 24-bit CRC. Okay. The base station will XOR. This is XOR with this particular string. User 1 RNTI. Okay. XOR and transmit. This is what is transmitted. Okay. Both user 1 and user 2 decodes them. Okay, user 1 and user 2 using the DMRS and all this thing decode them. Okay. So the decode, after the decode, what will happen? They will come all the way to the CRC. It will get the CRC, it will get everything. So both the users will get the same thing. Okay. Okay. So now what will user 1 do? User 1 will, just 1 minute. So now user 1 will XOR with his user 1 RNTI, the CRC. User 2 will XOR with his own RNTI, user 2 RNTI. Okay. What will happen? Because it is originally scrambled, with the user 1's RNTI. This will be small garbage. Okay. This will be CRC. Okay. Then he'll compute the CRC of this, and this CRC and this CRC will not match. Okay. Whereas this guy perfectly, if everything, assuming that the channel is all good and other thing, this will match. Okay. So the user will know that this data is for itself and not for itself. Whereas user 2 will discard this. Is this clear?
Yes, sir. Now it is clear.
Okay. So this is one of the ways in which, while the information is broadcasted, at least the users will know for which user it is intended for. Okay. So one thing you should remember, technically user 2 is discarding it, but his data is correct. The CRC is not matching because the CRC is scrambled by different RNTI, but the data is correct. Okay, so from a security perspective, this is not such a great thing. So what they do is they also do some scrambling also, the scrambling also, so that they cannot decode the data. The data, some parts of this are scrambled with some common RNTIs. That's known for everyone though. Okay, fine. So this is the PDC SCH transport channel. I'm not going to go into again.
Sir,
Please.
how the RNTI is allocated to a particular UE?
Okay, we actually saw that when we did the Praj. So after the Praj, fourth step. So Praj is the first thing. Praj, what happens in the Praj? You Praj, you join, then they extend the 4 steps happen, and the fifth step, what happens? An RNTI is allocated to a particular user. Okay, there are multiple types of RNTI, by the way. Okay, so for example, there is some data I told you yesterday, broadcast data, which some set of users have to decode. Okay, for example, corset 0 or a lot of users have to decode. So that is scrambled by a specific RNTI. Okay, a group RNTI will be, it's scrambled by that. There is some information whereas maybe 3-4 users have to, for example, decode. Okay, they are specified by some RNTIs. Okay, we'll get into this RNTI business in a little while. I'll explain. I might have a slide somewhere actually if you want. Okay, so you see you can see my slide now. So these are the different set of RNTI that are there. Okay. So CRNTI is a dynamically scheduled unicast transmission. It's UE specific transmission. It's there in downlink shared channel. Okay. Similarly, SIRNTI, for example, broadcast of system information. System information means SIB1 messages and other things. Okay, that control corset 0. When you're doing, you do it with SIRNTI. RARNTI is a random access response. Remember this RARNTI is that's something that is that is obtained by the random access response, obtain the RARNTI. So there are so many RNTIs. Okay, and this RNTI has some specific ranges. So what happens is we'll get into this RNTI business later. So RNTI, just in a brief, for a particular UV is allocated after the end of Praj procedure. There's a lot of RRC messages that are exchanged. One part of that is RNTI that's also exchanged. CRNTI exchanged for a particular UV. Okay. SIRNTI also will be exchanged as part of self broadcast information. It will be sent. Okay. RARNTI will be something that is between the particular UV and the particular base station. Will be dynamically obtained through the random access response. Okay, is that clear? Shall we go ahead?
So can we conclude that all the RNTIs for different purposes are allotted by Z node B to the UE, and UE use it for scrambling particular signal?
The base station is using for scrambling. The decoder, of course, the UE also uses the same thing. Yeah, what you say is true.
So, but allotment is done by
base station.
Base station, and it is
always
and all the
everything is done by base station. Yeah.
Right, and all the RNTIs are dynamically allocated. There is nothing like it is fixed. Some RNTIs are fixed, and that UE or
for example, system information RNTI are fixed. But again, that's also decided by the base station. But once it is decided, just keeps it like that.
Okay, that is kind of a one-time allocation, and some of the messages are every time allocated a different RNTI.
Different RNTIs, yeah.
And
but the system RNTI also can be changed by the base station. It's up to the base station.
Okay, fine. And these RNTIs are mainly used to scramble some of the signals, right?
Exactly. So scrambling of information and understanding. So for example, how do you identify a user at the physical layer? You can use it by using his RNTI.
Right. So how do you know that you have to scramble a particular signal by a particular RNTI, or it's a trial kind of, you try with all the RNTI you have, and then if you're able to scramble with particular, then you understand. Can you explain that?
Yeah. So essentially, see, PDCCH. Essentially, think of this. Who is this, by the way? Sorry.
Sir, I am Ashok Kumar.
Ashok Kumar, sir. So what happens is, so now we are in the downlink, and the downlink, the base station has to send information for different scheduling for different users.
Yeah.
Okay, so let me just explain this in iPad. Anyway, this will be useful when we
Can
go.
we just look at attached process and their the way RNTI used? If you can explain, it will be clear to us. Only one process, maybe attached process or any other process which you may like.
So let's do this. Okay, so there are 3 UVs. Okay, let's assume there are 3 UVs. Okay, so the UVs have finished their patch procedure and they have joined the network. So everyone will have one RNTI. Okay, so I'll call this RNTI 2, RNTI 3, RNTI 4.
So this RNTI is which RNTI? Because there are many types of RNTI.
This is CRNTI. I'm just talking
about
CRNTI.
So basically, the CRNTI is the temporary cell, right?
No, it's a UV specific RNTI. CRNTI is a UV specific RNTI.
Okay, so it identifies a set of UVs or
one specific UV. One specific UV.
One specific UV.
Okay, so you can see that there's CSRNTI, which is cell specific.
Okay. Fine.
You can see
that's
this.
Okay. That's okay. So
okay, I mean, see the okay. So once you have this, the base station of course knows this. The base station knows that this UV corresponds to, it has a mapping UV1 corresponds to RNTI 1. These numbers, RNTI numbers are not correct. I mean, I'm just giving an example. So UV corresponds to RNTI 3. UV3 corresponds to RNTI 4. Okay, so the base station knows this.
So it will be one of the 16 hexadecimal numbers, right?
One of the 16 hexadecimal. They give a range. You have to choose the range.
Okay.
So now what happens is, now the base station wants to send control information to these 2 UVs. Okay, it scheduled these 2 UVs, so it wants to send control information.
Right.
Okay. So what will it do? It will put a core set for this one. It will put a core set in some such space for the other one. Okay. So for example, this is for user 2, UV2, and this is for UV3. Okay.
Right.
What will this do? This will scramble this one. This will scramble this with. This will scramble this with.
RNTI, particular RNTI.
RNTI in this case. Okay. This will scramble this with RNTI 4.
Right.
Okay. It sends it off. It brought. I mean, now it's all. It came all the 3 guys.
So all the 3 will receive and they will try to scramble using their code. If they are able to, that means that is meant for them. Otherwise, they will drop it, right?
So, for example, see, user 1 will try to decode both this. He'll fail. User 3 will decode this and this one. Yes. User 3 will decode this one and try to decode this. What will happen? This will fail, whereas this one will succeed.
Right.
Okay. User 4 will try to again decode both. So user 4 will succeed here. Okay. So there's one more thing I want to teach you here is that this is a blind decoding. This is what is called as blind decoding. In the sense that they actually don't know at which point which core set corresponds to which way.
Right. So UV only knows the location from which it has to extract the information and then unscramble. So only UV knows that it has to look for which time and frequency location.
Exactly. So I mean, I will come to this. They simplify it a little bit further so that the UV doesn't have to do everything. So many of these things it has to decode. They introduce the notion of something called a search space. I'll come to that in a minute. Okay, in the later slides. Okay?
So search spaces are already specific. So
specific. They tell you, okay, if you, I mean, I will explain you that when we go to that point. It will become clear. Okay, they simplify this a little bit.
One very general question here, that why GNodeB cannot use the other IDs which UV is having. For example, it may have SUPI, SUKI, etc., which is used when it talks to the control plane. But at radio side, why? I mean, that cannot be used or not preferable, or we are using RNTI. That's a basic question.
See, I mean, I'm not very sure of that thing. See, one thing that I feel is, see, SUPI and all these are higher layer parameters. The physical layer actually doesn't know these things. Okay.
There could have been a process where it
could have been a process in which they could have known this, but I'm not very sure. That's actually a very good question. Why can't we use the specific identity? One is, of course, those SUPIs and all things are higher, larger number of bits also. One thing. IMEI and other things are larger bits. I mean, they're more bits. But saying that, what you said is absolutely true.
Okay.
One more thing happens is, okay, let me find out the answer to this. I mean, this has something to do with some legacy issues implementation. I have to find this out. Why they can't?
Yeah, yes.
Why do they implement this RNTIs like this? Okay.
Right.
Okay. So, I mean, I'm not going into get into the polar code and rate matching like what we did for LDPC. So what I'm going to do, ask you is, if you are interested, the same Professor Andrews lectures that we saw for LDPC, they also have lectures for polar codes and of course the rate matching for the polar codes. I would suggest you to please look at them, and of course you have to read the specification, then it will become clear. Very similar. I mean, of course, the rate matching part and other things are similar, but polar code is different. So those of you are interested in understanding this, what you should do is you should actually check that out. Okay, you should actually check Professor Andrews' lectures. Okay, maybe someday I'll add this transport channel, but let's go forward. Okay, so before we go forward, I want to once do this. Okay, let's go. Let's start this. Okay, let's start with the notion of what is something called as a corset. Okay, so corset is a time frequency resources where a UV searches for control information. Okay, corset is nothing but essentially it's a set of time frequency. It's a subset of the time frequency grid where the UV does the search. Okay. So corsets, I mean, there are some corsets that are configured at the cell level for broadcast, and there are some corsets that are configured at the UV level. Okay. So a corset can have up to 3 OFDM symbols. It can be anywhere in the slot. Okay. In general, corsets are generally put in the beginning of the slot. Okay. The reason is that until unless you decode your corset, the control information, you cannot decode the other data. Okay. So what happens if you put the corset at the end of the slot? You have to wait till all the OFDM symbols come. The 14 OFDM symbol comes, and then only you'll be able to decode the data, which increases your latency, which increases your storage space in the physical layer, and all those things happen. So generally, people put corsets only in the beginning, but the specification does not prevent you from doing that, from putting it anywhere. Okay. So the number of resource blocks in the corset is given by NRB corset. Okay. Again, these are specified. We will look at the specs in a little while. So what it turns out is the number of corsets per bandwidth part is limited to 3 for the UV. Okay, you have to configure this, and the number of corsets per bandwidth part is limited to 3, including the common and the UV specific corsets.
So when we say 3, it is what? Like, for example, if you look at time symbol and subcarrier. So when we say 3 BW, I mean limited to 3 means what? 3 symbols or 3 subcarriers or what?
3 is limited to 3 corsets. Okay. So what?
So that means 3 corset means at the 3, because you are saying that the symbol is say 0, 1, 2. The three symbols are being used. Now how many subcarriers that is also defined, or how many?
I will tell you. I'll explain.
Okay.
So suppose this is the entire bandwidth. Okay. So this is the bandwidth part. I mean, maybe in that the bandwidth part of the particular UV might be from here to here, for example. This is the bandwidth part. Okay. Right. Then you can define a corset, for example. This can be one corset. Okay. This can be the second corset. Okay. So the UV will search only in these corsets.
So that means when you are saying 3, it is the frequency domain, because symbols are say fixed 0, 1, 2.
No. Symbols can also be different. By the way, I mean, I'm just showing you like this because it's the most easiest, but this can also be true.
Okay. But generally, we have seen that initially
it's put in the only first 3 symbols. Yeah.
First 3, because initial deployment will be along with 4G, and in 4G also you have first 2 symbols, first 2 perhaps.
No, even in NR also, it's mostly will be 2. Okay.
Yeah, even 1 is enough in some cases.
Exactly. Yeah. See, it's up to 3 OFDM symbols.
Yeah, up to yes.
Okay. Yeah. See, the thing is in LTE, what
So how
happened is,
many? So it is not clear to me how many RB or the frequency sub-carriers will be used generally. If you can clarify that
yeah,
also.
as we go forward, I'll tell you. I'll tell you
Okay,
this. Okay.
fine, fine.
So one more thing I want to tell you was in LTE, it's dedicatedly the first two symbols are always for what do you say?
Corset, yeah.
For the control information. It's not
Yeah.
called a corset there. The control information. You can also extend that to 3 by using some control, some other flag. I forgot the flag's name. You can extend that, but generally people use 2. In 5G, they have limited the corset to what do you say? Only 3 OFDM symbols per corset. Okay, but the thing is, the corset can be anywhere. The flag in 4G is called as PCFICH. PCFICH. Okay? And the number of symbols can be changed in there also, but it's complicated. In 5G, it's a little bit more UV specific thing. I mean, you don't send anything if the UVs are not there. That's why they introduced the notion of a call set. Okay. So before we study chord sets, let's understand. I want to show you one diagram so that things become a little bit. This is a very important diagram to simplify our ideas of what PDCCH channel is. Generally, PDCCH is the most confusing channel of all things. Okay. So I'm going to draw a diagram and then I will explain you what this is. It's called the downlink. DCI stands for downlink control information. There are multiple format 0, format 00, format 01, format 10, format 11, so on and so forth. There, okay. DCI control. Aggregation level. Wait, just hold on a minute. I'll write this. Aggregation. This is called PDCCH. Let me explain you this whole diagram. Okay. See, finally, control information is what? A set of bits that you want to send to the UV. Okay. I mean, of course, the set of bits have certain interpretation. I mean, it will tell the first bits are this, for second bits are this, 10 bits are this, so on and so forth. Okay, but they're at the end, they're set of bits. That's all. Okay. And these bits come from where? Bits, the DCI transport channel gives you these bits. Okay, this is the PDCCA transport channel that we looked at. Okay, so there are multiple formats for these bits. One is called the format 00, format 01. That's downlink information. So the uplink allocations, and format 10 and format 11 are the downlink information. Okay, and similarly, the format 20, 21, 23, 22, and 23, which are common signaling information. Okay, so these are formats. What are formats? Formats are nothing but a certain arrangement of bits. Finally, there is bit string of bits that comes. Each of this have certain lengths and they're variable lengths. Actually, they're variable lengths. Okay, good. Now, these are bits that came. So now what will happen? So now you have to allocate. So as a base station, you know whether a particular UV is in a bad or a good signal. Okay, suppose the UV is very far apart, far. Then what will happen? then the SNR will be low. So you may want to do low code rate. Low code rate means essentially you want to put more parity bits. Okay. And what you do is, so this format 0, for example, let's take format 1, format 10. Okay. Let's take the example of format 10. Okay. So format 10 may have 130 bits or something. I mean, just giving example. These are, for example, this is not concrete. I mean, I don't know exactly how many bits it has, but 130 bits. Okay. So what will happen? For a user who is far, you put a low code rate. Okay. So after coding and other things, what will happen? This will extend to maybe 600 bits. Okay. Maybe you put a very low code rate. Whereas for a user who is close, this may extend only to 260 bits. You may put half code rate, whereas here you put 1/4 code rate. Okay. So now these bits have to be mapped to certain resources. Okay. So that is called the aggregation level. So what does the aggregation level tell you is number of, I mean, in CC is what is CC called as control channel elements. Okay. CC represents something. One CC is 72 arrays. Okay. We'll come to that later. So this is a block. So you have to allocate control channel in terms of blocks. Okay. So what you do is for a user who is far, okay, or requires more control information, the base station allocates more number of CC. Okay. So for example, this might be allocated some 10 CC. I mean, 10 is not there, maybe 8 CC. Okay. Maybe this might be allocated some 4 CC. Okay. So once the CC is allocated, you take this 130 bits and rate match it to the CC. The number of CC that you are allocated to. You do the rate match. Okay, but you find the code rate and other things so that you can fill up this 8 CC. Okay, so that is called the aggregation level. Okay, so generally what is aggregation level? Generally what happens is a base station allocates higher aggregation levels to the UVs with lower SNR. Okay, for the same format. Of course, if they require more data, of course they'll allocate more higher aggregation level. But in general, what happens is an aggregation level, a higher aggregation level is allocated to UVs with lower SNR so that they can recover the data, I mean, with the lower SNR. Is this clear? Is this notion clear? Did you understand this part? Any questions? Okay. So you should understand the same format can be transmitted on multiple aggregation levels. Okay, because you do that because of rate matching and other things. I mean, which the transport channel does. Okay. Now you have all this. I mean, CC are actual physical things. So now you have to place them somewhere in the core set. Where you place them in the core set is determined by the subspace. Okay. Okay. So for example, you be remember of SIP0 core set 0. Okay, core set 0 was about the SIP message, SIP1 message. Okay, SIP1 message is a broadcast message. Okay, but see, SIP1 has allocations for the uplink allocations for the patch and other things. Okay, so you use a particular format DCA. Okay, so what you do is that you put that in the type 0 subspace. Okay, so what does the type 0 subspace means? Essentially, okay. What this means is, remember, core set, there was something called core set 0. We already saw this core set 0. Core set 0 has certain locations and other things. Okay, so in that core set 0, I mean, type 0 does nothing other than SIP1. So it's very obvious where there's no need of a big search space for that. So UVs will only search in that core set 0. In that core set 0, this will start at some point. This is a search space. This is the SIP1 search space. Similarly, type 1 is other SIP messages. Type 2 is paging. And and UE specific signaling is okay. So all of them will have such space. So essentially, these are subsets of the core set where you place this aggregation. Whatever you have got in the aggregation level, you place in those core sets, in those particular parts of the core set. Okay, so type 0 will have certain part of the core set, type 1 will have certain part of the core set, type 2 will have certain part of some core sets, type 3 will have some part of some core sets. Okay, all core sets do not have all types. Okay, similarly, UE specific also, you put them in some particular core set, you provide a subspace. Okay, essentially you're providing some subset of the core set. Okay, and then finally you map it into the physical space, which is nothing but the core set. Is this clear? This is clear, everyone? Hello? Am I still audible?
Yes, you're audible.
Okay. So you should keep this whole thing in mind when we are doing this control shell. Okay. So I'm going to talk about just aggregation levels. What are these aggregation levels? What are the CCEs? I'm going to talk about CCE to REG mapping. What is this REG? How do you map this aggregation level to core sets? Okay. Then we will look at subspaces. Okay. Given these are the CCEs that are there and these are the RE, I mean, how do you map the CCEs to these core sets? What is meant by subspace? Okay. Then finally, we will understand the formats of DCI. What are the uplink and downlink formats? Okay, that is how we are going to do. So keep this picture in mind. So DCI is actually bit level. Aggregation level is just, I mean, nothing but mapping these things to a certain number of CCE. Subspace is a subset of, you're choosing some subsets of the core set, some specific RE, I mean, REs and other things in the core. It's not RE, it's REGs. We choose something called REGs. Okay. Just keep this picture in mind while we are doing this next couple of lectures. Okay. Okay. So they have a notion of something called the resource element group. Okay. So a resource element group is nothing but one resource block in one symbol. Okay, a resource element group is nothing but 12 REs. Is actually a resource block. Okay. So how will it number? The numbering of the resource element group is a little bit different. Okay. Suppose this is your core set that has been allocated to you. Okay? So this has two symbols and some number of resource elements. Okay. So first you know what is resource block. So the resource block, so this 0 implies there are 12 REs in. Okay. This has 12 REs. This has 12 REs. This has 12 REs. Okay. So how do you number these resource blocks? You number the resource blocks first in increasing order of the symbols and then in increasing order of the frequency. So you number them 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 12. So this 12. And so this is how you number the resource element groups in a core set. Is this clear? And then you have the notion of something called CCE, control channel element. A CCE consists of 6 RAGs. Hello, any question?
Yeah, so this 0 means it is 12 resource element, right?
12 resource element. It's like a resource block. It's one resource block.
Okay. And that resource element has to be I mean, so I had to look at frequency domain. So 12 RE means in frequency domain or in time domain, I can take those REs.
No, in frequency domain. This is increasing frequency domain. This is time domain. So this is first OFDM symbol, 12 REs.
So when we say 0, it will be say in OFDM symbol 0, 12 number of REs, consecutive.
12 number of REs, yeah.
Consecutive REs, right?
Consecutive REs, okay. So this 1 means essentially the OFDM symbol 1.
And any 12 REs. So it could be anywhere, no? I mean, although consecutive REs, but it is located at some fixed locations, right?
It's located at some fixed location. Okay.
So meaning is that one REG, suppose REG 1 and REG 3 can be located at 2 different places. It need not to be contiguous, 1 and 3.
I think they should be contiguous.
Acha. Okay. So
I
has
think
to
they
be
should be
contiguous.
contiguous. They should be contiguous. Yeah.
Because it has to be in the range, so it will be contiguous kind of.
It will be contiguous. It will be contiguous.
Okay.
But
Fine,
I'll confirm
fine.
that. I'm more or less sure it's contiguous. But let me just confirm that once. Okay.
Okay, fine.
So you see. So the next notion is called the control channel element. A control channel element consists of 6 REGs. Okay, that's what they say. So each REG has 12 resource elements. So 6 REG has 72 resource elements. So in the core set itself, there are pilots. All these REs also are interlaced with pilots. I will show you the pilots also there. Okay. So the number of CCE depends on the number and the aggregation level. For example, if you have an aggregation level 1, you use 1 CCE. Aggregation level 2 means you use 2 CCE. Aggregation level 4 means 4 CCE. 8 means 8 CCE. And 16 means 16 CCE. Okay. So when they specify an aggregation level, essentially you take your data and put in those much number of CCEs. Is that clear? Is that fine? So I'm just going to skip a few slides and I'm going to download this. So the DMR, so essentially whatever we do in PDCC is always QPSK modulated. Okay. And every 4th subcarrier of the REG is a DMRS. The DMRS is also PDS. The DMRS is QPSK modulated. The DMRS is QPSK modulated. And every 4th subcarrier of the REG is also sorry, 1 minute. Every 4th subcarrier of the REG is a pilot, DMRS pilot. Okay. So let's count the number of useful subcarriers in CC. The total number of RE is 66 into 12 is 72. The number of DMRS is 1/4. The number of DMRS is 6 into 12 by 4, which is 18. So the number of REs, useful RE is 54. Okay, in a CC. 54 would correspond to, if you use QPSK, 108 bits. Okay, so each CC has 108 bits. Remember that.
So I have one doubt. So DMRS location symbols are fixed, right? So I think symbol 3, symbol 4, and symbol 11. So
no. That is for PDSCH.
Okay.
PDCC
this is DMRS for control channel. Okay, fine.
PDCC has its own DMRS.
It is for control channel. Okay.
For control channel DMRS.
Okay.
So this PDCC has its own control channel DMRS, and as I was saying you, if the density of the DMRS is 1/4. Every 4th RE is in its CCE is in its REG is a DMRS.
So if it is always QPSK, then why DMRS is required? So it's already known that a signal will be QPSK. Then for which other?
But channel, to estimate the channel, sir. To estimate and equalize the channel, we require the DMRS.
Okay. Okay, fine.
Okay. So the DMRS is also QPSK here. Okay. So one thing that I want to talk about PDCCH is single port transmission. Always a single port transmission. Okay. Okay. So let's get back to this. So each CCE has 108 useful bits. It consists of 72 RE. But once you remove the amount of DMRS, it has 108 bits. Okay? So if you use 2 CCEs, it means you can transmit 216 bits. 4 CCEs, so on and so forth. Okay. So depending upon your coding rate and other things, you may require more number of CCEs, or if more number of CCEs are allocated to you by the base station, then you rate match to that. Okay. Is this clear? Is this fine?
Yeah,
any questions?
Yeah. One question: when we say 6 REG, those whether I can choose say 0, 5, 8.
No. I'll explain you what are the REGs that are chosen. Okay, there's a specific format. Okay, what REG consists of which CC?
My question was about CC.
Combining CC to REG mapping is something called REG bundles. I will explain you what CC are mapped to which REGs. Okay, that's a complicated mapping is there. Okay, we'll go through this. So, okay, let's just at least do this part and then we'll stop the class, okay, for today. So how are the CC mapped to REG? So I told you CC consists of, each CC consists of 6 REG. Okay. So which CC consists of, I mean, for example, CC1, what REG does it consist of? CC0, what REG does it consist of? Okay. So there's a complicated mapping to that. Okay. So first, before we do that, we have to understand a notion of something called an REG bundle. Okay. So this bundle size, REG bundle size, I mean, resource element group bundle. Okay. REG bundle, it's called as. The bundle size is specified by parameter L, which is specified by higher layer parameter. Okay. It's called L. So here I show an example of an REG bundle with size 6. Okay. So in this case, for example, 6 means 0, 1, 2, 3, 4, 5 form one bundle, 6, 7, 8, 9, 10, 11 form one bundle. Okay, again here also 12, 13, 14, 15 form, 14, 15, 16, 17 form another bundle. Agreed? Okay. So this is called an REG bundle. Okay. So now the CCJ is mapped to the following REG bundle. Okay, it's given by a function. Okay. This function is a complicated function. There are two notions of bundles. One is called interleaved and another is called non-interleaved. If it is non-interleaved, the notion is very simple. A CC is mapped to that particular REG bundle. Okay. For example, CC is 0 is mapped to CC REG 0. CC1 is mapped to REG 1. CC2 is mapped to REG 2. Okay. If that is not the case, if there's okay, so the other case we'll look at it in the next class. It's a little bit complicated, but we have to learn that. What happens when L is equal to 2? Okay, so let's understand this when the bundle size is only 2, for example. Okay, then what will happen? This will form one bundle, this will form one bundle, 3 bundle, 4th bundle, 5th bundle, 6th bundle, 7th bundle, and 8th bundle. Okay, then L is 2, so 6 by 2. So for example, 0, CC 0 will consist of 6 by 2, 6 by 2 plus 1, and so on up to 6 by 2 plus 6 by L minus 1. Okay, we'll do this in the next class. I will explain you this using pen and a paper, how to do this bundle to this mapping. So finally, there's a complicated map between the bundles and the CCs. That's what you should remember, because we'll do this bundle mapping, so then it will become clear. Okay, so I'm going to stop now. I just want 2 minutes of your time. I'm just going to stop recording and then discuss this.